Hello and welcome to the Unit 6 Section 4 video on trigonometric ratios. Alright, do not let the word trigonometry scare you because trigonometry is not as hard as you think it's going to be. So let's just talk about what trigonometric ratios are. We're talking about similar right triangles because the angles are the same in the right triangles. We have 90-degree angles here, those are all the same, and a 32-degree angle in all of these. So that makes all of these triangles similar. So therefore, we can take our short leg, set up a ratio. Take our long legs, set up a ratio. We can take our hypotenuse and set up a ratio and get a similarity ratio out of that. Well, what if we compare the sides to themselves within the triangle? So in other words, what if we take BC and we compare it to AC? We take our short leg and compare it to our hypotenuse. Okay? Here, our short leg, we're going to call our opposite leg because it's opposite of the angle that we're looking at. We're looking at this 32-degree angle. If we go opposite here and we put that over hypotenuse, that's going to give us a trig ratio. Similarly, if we take the adjacent side, so we take AB and set it over the hypotenuse, that's going to give us a trig ratio. And then if we take our opposite and put it over our adjacent, that's going to give us a trig ratio. And that trig ratio is the same for this large triangle, the medium-sized triangle, and the small triangle because they all have a 32-degree angle in them. Okay? So let's take a look at what those trig ratios are called. So here's the big table with a lot of information. We're going to go through each of these one by one. The sine of A is your opposite leg over your hypotenuse. So in this figure, A is here. The opposite leg is side A, little a. Our hypotenuse is C because it's opposite of our 90-degree angle. So A over C is sine of A. Sine of B, if we go here, now we got to go to this opposite side, which is B, and we're doing B over C. Opposite side over the hypotenuse. Now, if we use the adjacent leg, cosine of A is my adjacent leg, B, over my hypotenuse, C. So cosine of A is B over C. Cosine of B is A over C because A is adjacent to B. And then the tangent of A is your opposite leg. So opposite leg being A over my adjacent leg being B. So A over B. The tangent of B is our opposite B over our adjacent A. So that's B over A. All trig functions are ratios. They're ratios of two of your three sides of your triangle. So let's take a look at how these work. In example 1, we're going to write each trigonometric ratio as a fraction and as a decimal rounded to the nearest hundredth. So, before we get into this, let me give you a little mnemonic to use. You can think of this as so, ka, toa. Okay? So, sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. Tangent is opposite over adjacent. So, ka, toa. If you can remember that mnemonic, you will be just fine in doing trig. So, sine of r is going to be equal to opposite over hypotenuse. So, r is here. The opposite side is 12. And our hypotenuse is 13. That does not reduce, so we can leave it as it is. If you put in your calculator, you do 12 divided by 13, you get approximately 0.92. The cosine of r is going to be adjacent over hypotenuse. So 5 over 13. That does not reduce, so we'll put our decimal form, divide it in your calculator, and you get 0.38. And now we're going to do tangent of S. So now we're moving over to this angle. It's going to be opposite over adjacent. So 5 over 12. That does not reduce either, so we leave it. We write our decimal, 0.42. Remember, when you're writing it in fraction form, it must be reduced. Do not leave it as an even number over an even number, for example. Always reduce it. All right, in example 2, we're going to use a special right triangle to write the sign of 60 as a fraction. Okay, so let's think about what sine of 60 is. Sine of 60 degrees is going to be our opposite over our hypotenuse. So our opposite side is s square root of 3. You remember that from a couple of sections ago, because this is a 30, 60, 90 triangle. Our hypotenuse is 2s. And when we cancel the s's, we find that the sine of 60 degrees is square root of 3 over 2. And that is always going to be the sine of 60 degrees. It is always going to be the square root of 3 over 2. All right, the next example is using your calculator to find each trigonometric ratio. And then you're going to round your answer to the nearest hundredth. So let's talk a little bit about how your TI-84 is going to work here. So here's my TI-84. I'm going to power it on, and you'll notice it's been reset. The RAM has been cleared. So this is something that you're going to need to check every time, because the default mode for a TI-84 is not in degrees, but in radians. So we're going to have to change our mode. So first thing you're going to need to do is you need to hit the mode button, which is next to your second button. And then you're going to go to the third item in your menu. That third item is on radians. You need to change it to degrees. So you got to switch over to degrees by hitting your over arrow, and you must hit enter to make that switch. Once you're done, you can hit second mode to quit. Now we're in degrees mode. Now you can do these problems. If we want the cosine of 76, you're going to hit the cosine button, which is right here, and then put in 76, close your parentheses, and hit enter. And now we have the value for the cosine of 76 degrees. And you round it, it becomes 0.24. If I want the sine of 8 degrees, I do sine of 8, hit enter, and there's my value. I round it. There's my answer. All you're doing is plugging it into the calculator. And then finally, for tangent of 82 degrees, I'm going to hit enter, and there's my value, just like you're shown here. And you're going to round that, and there you have it. So finding the sine, cosine, and tangent of some angle measure in degrees is not very difficult. You just put in your calculator and you find what your answer is. All right, on to example 4. We're going to find the length of each, and we'll round to the nearest hundredth. So we want to find the length of AB. So we're looking for a missing side. So we need to see what our relationships are. Well, this side is adjacent to 41 degrees. We are also given the opposite side. So since we're given opposite and adjacent, we're going to use tangent. So the tangent of 41 degrees is going to be our opposite, which is 6.1, over our adjacent, which is AB. We're going to multiply each side by AB, then divide each side by the tangent of 41. So I'll leave you to do that algebra. But when you do the algebra to rearrange, this is what you end up with. And then you can put this whole thing in your calculator. 6.1 divided by the tangent of 41 degrees. And you'll get approximately 7.02 inches. Because there are units in this figure, we will add units to that. All right, for MP, well, we're looking for MP. That's opposite of this angle measure that we have. We're given the hypotenuse, so we have opposite and we have hypotenuse, so our trig function is going to be sine. We're looking for sine of 20 degrees being equal to opposite, which is MP, over hypotenuse, which is 8.7. Multiply each side by 8.7, so you have 8.7 sine of 20. And you find that MP is approximately, when you put it in your calculator, 2.98 centimeters. And then for YZ, in relation to this angle, YZ is our hypotenuse. We're given the adjacent, so we're going to use cosine because we have adjacent and hypotenuse. So cosine of 38 degrees is equal to adjacent over our hypotenuse. Move YZ over, divide by cosine of 38, and you're going to get YZ is equal to 12.6 divided by the cosine of 38 degrees. Put that into your calculator, and you're going to get that YZ is approximately 15.99 centimeters. All right, example 5. This is a real-world problem. A contractor is building a wheelchair ramp for a doorway that is 1.2 feet above the ground. To meet ADA guidelines, the ramp will make an angle of 4.8 degrees with the ground. To the nearest hundredth of a foot, what is the horizontal distance covered by the ramp? So here, the figure is given for you. So in relation, we're trying to find what CB is. CB is the adjacent side to 4.8 degrees. You're also given the opposite side, the opposite leg to angle C. So we are going to be doing the tangent of 4.8 degrees, and that's going to be equal to opposite, which is 1.2, over adjacent, which is CB, which is what we're looking for. So the tangent of 4.8 degrees, we're going to divide each side by that. We can multiply each side by CB. You get 1.2 over tangent of 4.8 degrees. And you put that in your calculator and you find that CB is approximately 14.2904 feet. 2904 feet. So it says to round to the nearest hundredth. So our word answer here, the ramp covers a horizontal distance, of 14.29 feet. Okay. Now let's identify angles from trigonometric ratios. So let's talk a little bit about the streets in San Francisco. They are famous for their very steep streets. The steepness of a road is often expressed as a percent grade. Filbert Street, the steepest street in San Francisco, has a 31.5% grade. This means that the road rises 31.5 feet over a horizontal distance of 100 feet, which is equivalent to a 17.5 degree angle. That's fairly steep for it to be a straight road. If you think about it, 100 feet is about a third of a football field. So we are rising over 30 feet over the distance of a third of a football field. That is a very steep change. Now you can use trigonometric ratios to change a percent grade into an angle measure. So we're going to do that with example 6 here. We're going to use a trig ratio, cosine of alpha equals, or cosine of A equals 0.6, to determine which angle of the triangle is angle A. So we're going to determine, is angle 1 or angle 2 angle A? So cosine of A is going to be your adjacent leg over your hypotenuse. So adjacent over hypotenuse. So let's find what the cosine of angle 1 is. Well, cosine of angle 1 is going to be adjacent over hypotenuse. So that's going to be 3.6 over 6. Our cosine of angle 2 is going to be our adjacent here, 4.8 over our hypotenuse of 6. So for this one, this is 0.6, this one's 0.8, so therefore, since the cosine of A equals 60, equals the cosine of, equals the cosine of angle 1, then we can say that angle 1 is angle A. This all leads us into inverse trig functions. You have learned that the sine of 30 degrees is 0.5. Conversely, if you know that the sine of an acute angle is 0.5, you can conclude that the angle measure is 30 degrees. This is written as inverse sine of 0.5 equals 30 degrees. You may also hear this called arc sine, okay? So if you hear the term arc sine, it just means inverse sine. If you know the sine, cosine, or tangent of an acute angle measure, you can use the inverse trig functions to find the measure of the angle, and that goes for sine, cosine, and tangent. The easiest way to do this is use your calculator. So let's pull our calculator back out and take a look at what this entails. So let's take a look at inverse cosine. So you're going to use the second button and hit cosine, because you notice the blue text above is inverse cosine, and you're going to put in 0.5, and that gives you 60 degrees. And remember, make sure that you are in degree mode, not radian mode. The arc sine, so second sine of 0.45, is going to be 26.74, so that rounds to 27 degrees. And then finally, the arc tangent, so second tangent of 3.2, is going to give you 72.64, so round that up to 73 degrees. So now let's talk about solving right triangles. Using given measures to find the unknown angle measures or side lengths of a triangle is known as solving a triangle. To solve a right triangle, you need to know two side lengths or one side length in an acute angle measure. So let's see what solving a triangle looks like with example 8. And I want to show you two methods here. Here we are given two side lengths. So we could use the Pythagorean theorem to find the hypotenuse. So let's do that. A squared plus b squared equals c squared. A squared is 5. B squared is 7.5. And that's going to equal c squared. So you do this math, you get 81.25 equals c squared. And when you take the square root, this is AC. AC is equal to the square root of 81.25, which is approximately 9.01. Now, a word of caution. We're going to go find some angle measures now, but you cannot use your hypotenuse to do this because we have approximated our hypotenuse. So you are going to have to use the given leg lengths. And if we're going to use the given leg lengths to find the measure of angle A, then we are going to have to use tangent because we're going to have opposite over adjacent. So you're going to use the inverse tangent. Inverse tangent of opposite over adjacent to find that angle measure. Tangent will operate on angle measures. Inverse tangent is going to operate on your side ratio. And this is going to be approximately 34 degrees when you put it in your calculator. The measure of angle C, we do not have to use trig to do that because we have an approximate value for angle A. We know that angle A plus angle C is 90 degrees, so we're just going to subtract 34 from 90, and that's going to give us And technically, these are all approximations. So let's write these as approximations, because 34 is approximated. So that's approximately 56 degrees. So that's the first method to do this. The second method, we find our angle measures first. Okay? So I'm going to copy this and drop it in because it looks exactly the same. The work is going to be exactly the same. Okay, so the work is going to look exactly the same. So I'm just going to copy this and put it in. So all of that work is the same. We are now to the point where we can find our side length, our hypotenuse. And we're going to do it with trigonometry this time instead of the Pythagorean theorem. It's going to look a little more complicated, but I think you will be able to follow what's happening. So we know that the sine of A is equal to 5 over AC, because we have opposite over hypotenuse. Well, we know that we can rearrange this for AC. So 5 over sine of A. Well, what is A? Well, we know that the measure of angle A is approximately 34 degrees, but we cannot use the approximation. So instead, what we're going to do is we're going to use the inverse tangent. This is exact, this is approximate. So we're going to drop in the inverse tangent of 5 over 7.5 in for A. So we're going to have AC is equal to 5 over the sine of the inverse tangent of 5 over 7.5. And you can put all that into your calculator, and you're going to end up getting 9.01 out of that as well. So two different methods to be able to find the same thing. And really the only difference is in how you find that hypotenuse. Finding measure of angle A and the measure of angle C both work the same way in both methods. All right, example 9. The coordinates of the vertices of this triangle are given here. We're going to find the side lengths to the nearest hundredth and the angle measures to the nearest degree. So let's start with the side lengths. The easiest ones are JK, because that we can just count. 1, 2, 3, 4, 5. 5 units. And KL, which again is easy. We count that. 1, 2, 3, 4 units. But you are going to have to use the distance formula to find the hypotenuse. So if you use the distance formula, you're going to end up with 3 minus -1 squared plus our x's, -3 minus 2 squared. And that's going to give you, once you do all the math, I'll let you do that on your own. It's going to give you approximately 6.40. So those are our side lengths. Now let's find the angle measures. Well, the measure of angle K is easy because that's just 90 degrees. That's our right angle. The measure of angle J, we're going to use trig for. It is going to be, again, we cannot use our hypotenuse because that's approximated, so we have to use JK and KL. So if we want to find the measure of angle J, we're going to go opposite over adjacent. So we'll be using arctangent here. Arctangent opposite over adjacent, which is 4 over 5. Put that in your calculator and you get approximately 39 degrees. And if we know that angle, we can find the measure of angle L by approximating 90 minus our approximated angle from angle J. So 90 minus 39, and that gives us approximately 51 degrees. All right, let's wrap up this section and this unit by going back to San Francisco. Lombard Street is known as one of the crookedest streets in the world. The road's 8 switchbacks were built in the 1920s to make the steep hill passable by cars. If the hill has a percent grade of 84%, what angle does the hill make with the horizontal line? Round to the nearest degree. So recall that when we're talking about a percent grade of 84%, that we're talking about a rise of 84 feet for every 100 feet. Okay, so let's draw that in a figure. I'm going to draw a right triangle over here on the side. There's my right angle. And we are rising 84 feet for every 100 feet that we are traveling. Okay, 84 feet, 100 feet. So let's see what kind of angle causes that. So we're looking at this angle right here. So let's call this A. So the measure of angle A is going to be, we have our opposite and we have our adjacent, so we're going to have arctangent of our opposite over adjacent, 84 over 100. And that is going to be approximately 40 degrees. That is steep because, and that's the reason why you have the switchbacks, because an angle that steep, you're almost halfway to vertical. You're that steep, halfway to vertical with the ground. So that is the reason why you have the switchbacks on that road, because the switchbacks decrease the steepness that you have to go. All right, so that finishes off this unit, and that concludes the 3-unit stretch we have dedicated solely to triangles. Coming up in the next unit, in Unit 7, we are going to start to go into shapes, polygons that have more than 3 sides. So we're talking squares, parallelograms, trapezoids, kites, rhombuses, and then even beyond that, we'll go to pentagons and hexagons and octagons and things like that as well. So that's coming up in the next unit. But keep in mind, you are going to be using triangles a lot in the next unit because all of those shapes can be split up into triangles. So that's why we spent so much time on triangles. We'll move to higher order polygons in the next unit.